let's talk about something that sounds like pure science fiction. Building a complete human brain inside a computer. I mean, it sounds like an absolutely monumental task, something that borders on impossible, right? But what if that wall of impossibility is starting to crack? We're going to look at a brand new roadmap for what might just be one of the biggest projects humanity has ever taken on. And hey, if you think it sounds far-fetched, you're in good company. The author of the report we're digging into, Max Schantz, he admits that just a little while ago, in 2023, he thought the whole idea was absurd. And honestly, when you see the numbers, you'll get why. That skepticism is exactly what makes the latest breakthroughs so shocking. So what's a big reason for all that doubt? Look at this number, $21 billion. And get this, that was the high-end guess for just proofreading the wiring map of a single mouse brain, not even a human brain, a mouse. So you can see why the whole project felt like a total non-starter when just checking your work costs that much. Okay, before we get into how we might pull this off, we need to be really clear on what we're trying to build. You hear the words emulation and simulation thrown around a lot, but in this world, they mean completely different things. And nailing down that difference is absolutely key to understanding everything else. This analogy right here just makes it all click. A simulation copies the behavior. So think of an airplane, right? It flies, just like a bird, but it does it with engines and a metal frame. It isn't trying to be a bird. An emulation, on the other hand, copies the actual architecture underneath. It's like building a mechanical bird, with wings and feathers and muscles that all work the way a real bird's does. Both of them get you into the air, but how they do it is fundamentally different. So here's the bottom line. Brain emulation isn't about making an AI that just acts human. No. It's about building a program that actually copies the brain's physical structure, the neural wiring, how the neurons fire, the whole shebang. The goal here is to build the bird, not the airplane. Okay, so if the goal is to build this digital bird, what's been stopping us? Well, it turns out there have been 3 gigantic challenges blocking the path. For decades, these hurdles seemed so huge they were basically insurmountable, and it just stalled the entire field. These challenges really boil down to 3 things you absolutely need. First, you need the software, the math that can model how a neuron works. Second, you need live data, actual recordings of what neurons are doing inside a living brain. And third, and this is the big one, you need the map, a complete wiring diagram showing how every single neuron is connected to every other one. And this chart, this really shows you the insane scale of that mapping problem. A little fruit fly has about 140,000 neurons. Okay, a mouse, that jumps to 70 million. But a human brain, we're talking about 86 billion neurons. That leap in complexity is just staggering, and it's why this has been so incredibly hard. So what was the biggest roadblock in making that map? You might think it was taking the pictures of the brain, but nope, it was the proofreading. After a computer algorithm tried to trace all the connections, a human being had to go in and manually check for errors. For just one complicated neuron in a mouse, that could take 40 hours or more. It was the ultimate bottleneck. But this is where the story takes a huge turn. Remember how our author thought this was all absurd back in 2023? Well, that's because 3 recent breakthroughs just completely changed the game. Suddenly, the absurd started to look, well, possible. These are the 3 game changers. There's a new way to see brain tissue called expansion microscopy, a new way to label neurons called protein barcodes, and a super powerful new AI from Google called Pathfinder that just demolishes that old proofreading problem. And just look at the difference Pathfinder makes. It cuts down the amount of human proofreading needed by a factor of 80. What used to take hours and hours of tedious human labor can now be mostly automated. That one single bottleneck, the one that led to that crazy $21 billion estimate, it's just gone. And the other breakthroughs are just as clever. Take expansion microscopy. Instead of building a better microscope to zoom way in, scientists figured out how to make the brain tissue physically bigger. They soak it in this swellable polymer. It's basically the same stuff that's in diapers. And they literally blow it up. It makes all the tiny details super easy to see with a regular microscope. And then you've got protein barcodes. This idea is just brilliant. Imagine trying to trace millions of identical gray threads, all tangled up in a giant knot. It'd be impossible. But what if you could give every single one of those threads its own unique color? Well, that's what this does for neurons, and it makes it way, way easier for a computer to follow their paths. So, with these new tools ready to go, the path forward is suddenly so much clearer. For the first time, we can actually lay out a real roadmap with believable timelines and costs for how we get to full brain emulation. So, what does this new timeline actually look like? Well, the roadmap starts small. The goal is to fully emulate the brain of a zebrafish or a fruit fly sometime in this decade. From there, the plan is to scale up to a mouse brain in the 2030s. And if we hit those milestones, a full emulation of a generic human brain could actually be a realistic goal by the late 2040s. So what's driving this incredible speed? Well, it's economics. Check out this trend. Back in 1986, it cost over $16,000 to map one neuron. Today, for simple animals, it's down to around $100. This massive drop in cost is what's making these huge projects finally possible. And that translates to some pretty serious project budgets. The first full emulation of a zebrafish brain could be about $100 million. A mouse brain, that's $1 billion project. And the first human brain emulation, we're talking tens of billions. Now, these are huge numbers for sure, but they're not science fiction numbers anymore. They're in the same ballpark as other big science projects, like the Human Genome Project. All of this leads to a really profound question. What are these first digital brains actually going to be like? It's so important to separate the science from all the sci-fi ideas about, uploading your consciousness. And this is probably the most important takeaway. These first models won't be a copy of a specific person. It's not going to be your brain or my brain. Because the data has to come from many different sources, the result is going to be a generic, kind of baseline human brain. It's a map of our species, not of an individual. The whole idea of perfectly copying your personality, that's still a massive leap from here. So there you have it. What seemed totally absurd is now on the horizon. This isn't just about AI that can act like us anymore. We're talking about building programs that copy the very architecture that makes us who we are. And that leaves us with this huge question to think about. Are we right now the generation that's crossing the threshold from being a product of biology to becoming the architects of our own minds?